Hello. Hello and welcome to this video on collections of Rust. We are going through the standard collections. We have covered till now vectors, linked list, and hash maps. So we will continue with the hash set and then we will look at other ones. So if you want to see the source code, you can click this link and you can look at the source code and inspect and analyze. So we'll go through the documentation and we will cover the stable API, not the nightly API. So without further ado, let's get started. A hash set implemented as a hash map where the value is unit type. As with the hash map type, a hash set requires that the elements implement the EQ, equality, and hash traits. This can frequently be achieved by using derived, partial equal, equal, and hash. If you implemented these yourself, it is important that the following property holds. K1 is equal to K2 implies that hash of K1 and K2 should be also equal. In other words, if two keys are equal, their hashes must be equal. Violating this property is a logic error. It is also a logic error for a key to be modified in such a way that the key hash as determined by the hash trait or its equality as determined by the EQ trait changes while it is in the map. This is normally only possible through cell, ref cell, global state, IO, or unsafe code. The behavior resulting from either logic error is not specified, but will be encapsulated to the hash set that observed the logic error and not result in undefined behavior. This could include panics, incorrect results, aborts, memory leaks, and non-termination. We have an example. We use HashSet. We create a new object using the sort of constructor, and then we insert strings into the books variable which we created. We have string slices which we convert to string, and we insert 4 books. Now we check whether the set contains the books of winter, and we negate that condition. And if this results into successful one, that is, if this is false, so this negation will make it true. We print that we have books.lamp, that is 4 books, but the winds of winter ain't one. Then we remove the Odyssey, and if we iterate over the books, we can get the other 3 books. The easiest way to use HashSet with a custom type is to derive EQ and hash. We must also derive partial EQ, which is required if EQ is derived. Okay, so we have a struct Viking name string power usize, and we derive through hash EQ, partial EQ, and debug. Okay, debug is for printing. And then we create new hash set Vikings, and in Vikings we insert the objects of Viking. Einar to string power 9, Einar to string power 9, Olaf and Harald with power 4 and 8 respectively. And when you iterate over the Vikings, you get these objects, and this struct Viking will be printed. A hash set with a known list of items can be initialized from an array. So Viking names, which will be a hash set, can be initialized from an array containing Einar, Olaf, and Harald. Now we look at using in const and static. Like hashmap, HashSet is randomly seeded. Each HashSet instance uses a different seed, which means that HashSet new cannot be used in const context. Construct a HashSet in the initializer of a const or static item. You will have to use a different hasher that does not involve a random seed, as demonstrated in the following example. A HashSet constructed this way is not resistance against hash denial of service attack. So we import HashSet. We have from HashSet we have build HashSet default HashSet, and then we have mutex from stdsync. We will study about mutex when we study multi-thread programming. So we create a const empty set. We have HashSet string, and we pass build hasher default, and we type of that is default hasher, and we create from this hasher uh, a new hasher with hasher. And then we have static set. Static is requires the mutex. So like previous one, we have this hasher, but now it is wrapped in a mutex. Now we will look at some functions of HashSet. So first we have some implementation by which you can create HashSet objects. So first we have new, it creates an empty HashSet. The HashSet is initially created with the capacity 0, so it will not allocate until it is first inserted into. This we have already seen. The type here determines what kind of elements you can insert. Then we can create with capacity. So it will take capacity and will return a hash set of type T. Creates an empty hash set with at least the specified capacity. The hash set will be able to hold at least capacity elements without allocating. This method is allowed to allocate for more elements than capacity. If capacity is 0, the hash set will not allocate. So again, an I32 hash set is created with capacity 10. And if you check the capacity of this set, it will be greater than or equal to 10. Then we have new underscore nightly API. We are not going to consider. Then we have with hasher. Okay. In general, you won't use this. So create a new empty hash set, which will use the given hasher to hash keys. The hash set is also created with the default initial capacity. Warning, hash set is normally randomly generated and is designed to allow hash set to be resistant to attacks that cause many collisions and very poor performance. Setting it manually using this function can expose the denial of service attack vector. The hash builder path should implement the build hasher. Wait for the hasher to be useful, see its documentation for details. So we use the random state hasher, and we create an object of that, and with hasher function takes the random state hasher, and you can create a set. And then you can go on inserting elements and so on. Another constructor would be with capacity and hasher. So it will take both capacity and hasher. So the detail here is basically a combination of last two functions. And similarly, you have the usual syntax for that. Now we will look at, this is nightly API. We'll look at capacity. It returns the number of elements the set can hold without relocating. So this we have already seen in one of the assertions. We create with the capacity 100, and then the capacity will be greater than or equal to 100. Then we have iter, which will give us an iterator, as you know from our previous discussion of collections. An iterator visiting all elements in arbitrary order. The iterator element type is %, single quote lifetime of A, and type T. So suppose we create a hash set with this new, and we insert two elements A and B, and we iterate and we get X from the for loop, then it will give us A and B, but it can print in any order, AB or BA. Performance in the current implementation, iterating over set takes O capacity time instead of O because it internally widgets empty buckets too. So this you have to keep in mind. Okay. Now we will look at the len function, which returns the number of elements in the set. We have already seen the len function in vector and other hash map or linked list. So len will give the number of elements. When you create a new hash map, the length will be 0, and as you insert elements, the length will grow. Then we have empty, which will return true if the set contains no elements. So we have a new hash map, so it will be initially empty, and if you insert elements, it will become false. Then we have drain. So like hash map, this clears the set, returning all elements as an iterator. Keep the allocated memory for the use. If the return iterator is dropped before being fully consumed, it drops the remaining elements. The return iterator keeps a mutable borrow on the set to optimize its implementation. So we have created a hash set here with an array 1, 2, 3, so it won't be empty. And if you drain, you will get all the elements here in any order, okay, in arbitrary order rather. and after that set will be empty. Then we have extract if, which will take a predicate in the form of a mutable closure. Creates an iterator which uses a closure to determine if an element should be removed. If the closure returns true, the element is removed from the set and yielded. If the closure returns false or panics, the element remains in the set and will not be yielded. If the return extract if is not exhausted, example, because it is stopped without iterating or the iteration short circuits, then the remaining elements will be retained. Use retain with a negated predicate if you do not need the return iterator. So for example, like hash map we have seen, we split the uh, hash set. We have split this in hash map in odd and even. Similarly, we will split this into odd and even. So we create a hash set of I32 by creating from 0 to 8. So 8 will be not included. It is a half closed, half open interval. 0 to 7 will be included. So this will be collected from, this is from iterators. So the hash set will be created. Then we have extracted. And our closure is we take the element and we check if it is even or not. And we collect it. So now we have extracted, this will be an iterator. So we iterate over it and collect it into a vector, and then we will have evens and odds. Okay, we similarly iterate our set and we collect it, and then we sort evens and odds. So we will have 0, 2, 4, 6 and 1, 3, 5, 7 in the vectors. Then we have retain, like extractive, it will take a mutable closure, returns a boolean. The closure returns a boolean, retains only the elements specified by the predicate. In other words, remove all elements for which the closure returns false. The elements are written in unsorted and unspecified order. So here retain requires it to be even. So only even elements will be retained in this. Okay, after that 1, 3, 5 will be dropped. In the current implementation, as we discussed when we went through the iter one, the operation will take O capacity instead of O_len because it internally visits empty buckets as well. Then we have clears the set, removing all values. So this is quite simple. Then we have HashSet, return a reference to the set's build HashSet. So here we have the similar code here. We have random state. We build a HashSet object and we create a HashSet with HashSet. And if you call set.HashSet, it will give you the HashSet object here, okay, which will be of type random state. Then we have reserve, okay. So it is a method and it takes a parameter additional. So reserves the capacity at least additional more elements to be inserted in the hash set. The collection may reserve more space to speculatively avoid frequent reallocations. After calling reserve, capacity will be greater than or equal to self.length plus additional does nothing if capacity is already sufficient. So we create an empty hash, we reserve 10 and the capacity will be greater than or equal to 10. Then we have try reserve, it will return an result num. So this return okay, it didn't return anything. Okay. So try reserve will return a result num because it can throw an error. Tries to reserve capacity for at least additional more elements to be inserted in the hash set. The collection may reserve more space to, so it's the same detail. After calling try reserve, capacity will be greater than or equal to self.length plus additional if it returns okay. Does nothing if capacity is already sufficient. If the capacity overflows or the allocator reports a failure, then an error is returned. So we have HashSet new here. We create an I32 HashSet. We try reserve for 10 elements, and we expect that if it throws an error, then we print a message. Why is the test harness moving on a handful of bytes? Okay, so it will print this message and load out. Then we have strings to fit, like hashmap. We have this function, and I think vector also had this function. I mean, list as well. shrinks the capacity of the set as much as possible. It will drop down as much as possible while maintaining the internal loops and possibly leaving some space in accordance with the resize policy. So we create a hash set with capacity 100. We insert two elements. Capacity will be greater than 100 at this moment. And then we call shrink to fit. At this moment, the capacity can go as low as 2 because that is the minimum we need. Then we have shrink to, which takes an an argument min capacity of type resize. Shrink the capacity of the set with the lower limit. It will drop down no lower than the supplied limit while maintaining the internal rules and possibly leaving some space in accordance with the resize policy. If the current capacity is less than the lower limit, this is a no OR. So we create a hash set with 100 elements. We insert 2, capacity will be greater than equal to 100. We shrink to 10, capacity will be greater than equal to 10. If we shrink to 0, then capacity will be greater than equal to 2. Okay. Then we have the mathematical difference functions, okay, for which set are actually needed. So we have difference function. It will compute it computes the difference between two hash sets. So it takes other argument of hash set of similar signature TSA. So this TSA, if you forget, then it will be this TSA it is talking about. Okay, where T is the type of the hash set, S is the hash set, and A is the allocator. So where were we? We were at difference. Okay. All right. So you create two hash sets, 1, 2, 3, and 4, 2, 3, 4. So this 4 will be 4 will occur once only. Okay. Sets elements are unique. So you iterate over a loop and you call a dot difference and you pass b as a reference. And we iterate over the elements which would be a minus b. So it prints 1. Now we can compute the difference and collect it, and then we can we create an array of element 1, we iterate over it and we collect it. It will be same as this difference. Note that the difference is not symmetric. B minus A means something else. So B minus A will be 4 here. Then we have symmetric difference. This is all mathematical notations. It's the value representing the symmetric difference, that is the values that are in self or in other but not in both. So here, if you compute the difference which are not in both, so 2, 3 are in both, but 1 and 4 are not in both. So you will have 1, 4 as the result of symmetric difference. Then we have intersection, which will give you the common elements. It's the value representing the intersection, that is values that are both in self and other. When an equal element is present in self and other, and then the resulting intersection may yield references to one or the other. This can be relevant if T contains fields which are not compared by its PQ implementation and may hold different value between the two equal copies of T in the two sets. So if you intersect it, you will get 2 and 3, as you can see in the version. Okay, I think I'll stop here and we will cover remaining of HashSet in the next video. So the general idea is that why are we reading this documentation is to not memorize everything, but to become aware about where should we go if we land in trouble. Okay. What I mean by landing in trouble is, suppose we are going to use something, or we are writing some code, okay, and our ID completes, auto completes everything, and something goes wrong, it doesn't work, and we need to debug it. So before you can debug it, you need to be very clear about the code, that what it is supposed to do. And for that, you need to look at the documentation. So if you're not clear about what symmetric difference does, or what difference does, or what tri-with capacity does, and so on, you will not be clear that what the output of debugging should be. So before you can debug, debugger won't work without your logic. So to have very correct logic, we need to be aware that what the documentation gives us. So the idea is that we can revisit the documentation, but we have to be aware. Sometimes what happens, we end up doing the same thing which the library already provides, okay? Because we don't know that the library provides it. So the idea is that we know that what the library is giving us so that we don't implement it. So there are two objectives of service documentation. So I hope that you have learned something from this read through and it is useful for your studies. So we will meet again after 4 days, possibly. That is, if I don't miss any day, then we will continue this and we will finish this in the next video. Till then, stay curious, keep learning, and most importantly, enjoy.